Okay, so today is the last class for 3264. Yay! We are going to cover about the unsupervised learning, specifically about your EM algorithm. So EM is basically your expectation maximization. It comes down from two main steps. The first step is where we actually compute the expectation. Then we try to maximize this expectation. That means we try to iterate through finding the next set of parameters, get the higher expectation value, so on and so forth. Then we reach until convergence. In essence, that is the algorithm. Okay, so this algorithm is there. Anyone knows why we need this expectation step or not? Why the expectation step is kind of necessary? This one is solely because remember that in unsupervised learning, we don't have the target labels, right? So then we will have to substitute it by some certain latent variables. That's where we put some assumption. If I have this certain latent variable z, I assign this to a certain label, get what is the expectation, then I will update the labels again until eventually I would reach the convergence. That's why this is kind of like I compute here, then I want to find the next set of parameters that will maximize it. Okay, so this all works because of the fact that there's a latency here, plus we will always go towards the direction that will increase the likelihood of this function. That's why it will eventually converge. Okay, so you can check more in the lecture here. I will not go through much of the math for section 1 because section 1 in essence is just, I feel it's just a lecture slide but with the LaTeX form for the math itself. So yeah, I will not go through this much, but the main steps, we are going to cover it in today's tutorial, especially in this question, where we discuss how we can actually apply the EM algorithm to find out what is the parameters for this new mixture model, which depends on the exponential distribution. Okay, so feel free to get a donut if you haven't. Okay, so here we have our general EM algorithm, still the same thing, but today we are going to explore about this thing called the exponential mixture model. So we have seen that mixture of Gaussian models. This part is essentially if I have a certain distribution, I can just put multiple Gaussian centers, depends on how many centers I want to put. So that is usually parameterized by our K. Okay, so you can have something like, say for instance, if I want to model this kind of distribution, say I have like, these are my data points, then I want to check whether one point is considered an anomaly or not. So if I put something like, if is this an anomaly, then obviously this might be an anomaly from our pattern. But how do we quantify this? That's where we, in the lecture, we discussed that we can put multiple Gaussian distributions. So we can have like, say for example, one Gaussian over here, then we can have say another Gaussian over here, then this will model out our distribution. In fact, that is how we can model complex distributions. By putting a large number of Gaussian models together, then we take what we call the linear combination of Gaussians. Okay, so in essence, our GMM is essentially the linear combination of Gaussians. Now we are going to apply the same concept, but here we are going to apply it towards the model which uses an exponential distribution. So let's just look through the problem statement together. We want to derive the exponential mixture model. From the name itself, we will see that the only difference is simply one uses the Gaussian distribution, whereas the other one, it will utilize your exponential distribution. Okay, so here we define K as the number of mixture components. Then for each n from 1 to capital N, this kind of like the number of data points you have, we want to model the latent variable as a categorical distribution with this parameter pi. Okay, so this pi itself is a vector of dimension k. K itself is kind of like the number of mixture components or number of classes that you will have. Then we want to see that we denote z n k equals to 1. This is if you have a nth point and belongs to the kth component or the kth mixture. Okay, so if I have a point n and it belongs to mixture k, then the value of z n k will be equal to 1. So you would see that this zn itself is actually similar to your one-hot encoding, whereas there will only be one value that will be equal to 1. That's your znk if this is part of mixture k. For every other k that is not part of, that zn is not part of that mixture, then the value will be 0. Okay, so that's how we define this. Any questions so far? Okay, then we model the xn. Xn is m dimensions here. This will be an exponential distribution with parameter lambda k. So anyone remembers what is the formula for exponential distribution? If we say that some x follows say exponent of lambda. What does this mean? Formula. So if I want to find the probability of x, given this lambda that I already have, this will be equal to, this will be lambda times e raised to negative lambda x. Okay, so this is the definition of your exponential distribution. In fact, we will see this a lot today. Okay, so as long as you have the exponential distribution, then this will work. However, do note that the parameter given to us, this lambda k itself is a factor. Okay, lambda k is a factor. That means this will tell you for one particular k, okay, for one particular k value, this is the parameters lambda, which is of m dimensions, because it will be associated to each of the x features. Okay, so this lambda k itself is a factor. So if we want to find the probability of a certain xn, so note that this xn is a factor, I want to determine the probability of xn m for every single component of xn, multiply them. Okay, so that is how we model here. If I want to find the probability of this factor xn, then I will get for each component of that xn, apply to the exponential distribution. Then we multiply the result. Okay, where this pxnm is essentially your exponent lambda km. Okay, so that means for this lambda k for one particular mixture, I want to get the mth component multiplied with the mth component of x. So we multiply that. Okay, go inside. Any questions so far? Okay, so now we move on to problem 1. Problem 1 is we want to identify what is the set of parameters. So for us to model this as a mixture of exponential models, how do we quantify this? How do we put it in the parameters? Maybe so that you don't get brain stuck, feel free to get one donut from the middle if you haven't. Okay, what parameters do we need to model the EMM? Remember that in the lecture we discussed that we need two kinds of distributions. What are those? First one is we will have to, since we are going to introduce the latent variable, right? The hidden unobserved variable. So at first we want to also assume first, what will be the initial distribution of this latent variable? In essence, we want to determine what is the prior. Okay, so the prior is essentially just your normal P of Z or P of Zn. Okay, so we have to define this prior first. What distribution must it follow? By lecture? Note that this latent variable itself is going to be, you can imagine it if you, can I check if everyone understands k-means algorithm? K-means? K-means is a naive way where I want to find the centroid of each point. Then once I have I assume certain labels, then I just shift the label around until it reaches a certain centroid, right? So that's your k-means. So for now, we assume something similar, where your latent variable itself, this will be depending on, for each data point, which mixture model does it belong to? Okay, let's say if I have, this is my points, say I will have something like this. Maybe more dense here, more dense here. Okay, so obviously if I want to create some of the Gaussian mixtures, then the mixture would have something around, this will be the Gaussian center. Then this will be another Gaussian center. Okay, maybe I put another color. So the Z itself would actually denote, say, for this data point, does it belong to the mixture model centered around the orange one, or does it belong to the mixture model centered around the green one? Okay, so that is essentially our Z value. Then you will notice that for each value here, for each point, your Z will only range from 1 up to the maximum of K, because we only have K mixture models to be inserted. Okay, so from this point, you should notice that this prior will end up following what we call the categorical distribution. Okay, so this prior will eventually follow the categorical distribution. Reasoning is because you want to assign the Z itself to, your Z itself has to be assigned to one of the models, right? From 1 to K. Since this models itself is already discrete, it's not continuous, then That's where we apply the categorical or multinomial distribution. Okay, so that's the first thing you should observe. Your prior itself will follow your categorical because you have multiple labels. Okay, else if you only have one label, then you can just put Bernoulli, that's it. If it's only 0 or 1, then Bernoulli. But since we want to assign it to labels from 1 to k, then this will be your categorical. Okay, any questions? Then the next thing we want to set is also to determine what is the likelihood function, which is your p of x given z and the parameters. Okay, something like this. So which likelihood function do we follow for this one? If we are handling the Gaussian mixture, then we are going to use the Gaussian one, right? So for this one, what do we use? We're going to utilize the exponential distribution. So that is where the simple change happens. Instead of following a multivariate Gaussian, what we follow here is going to be, this is going to be the exponential distribution. Okay, but exponential of what here? Notice that we are only concerned about this whole xn. It will have m different components, right? Because it's a vector. Each of the component will have this distribution, your exponential lambda km. Okay, so in total, if I have this xn zn, I would say that this must be associated with, for every single component, I want to determine this xnm given your zn. Okay, so I want to determine for every single component of my xn. That's for my likelihood here. Which again, this part we know that this will follow through with your exponential distribution. So this will already follow your this will be your exponential of this will be exponential of lambda of xnm given your lambda k. Okay, so this is telling you that for the m component of xn, this will follow the distribution of exponent lambda k for that component m, because your lambda k itself is going to be a vector. Okay, so now we have already the prior and also the likelihood. Then we can now finally determine what is the set of parameters. Notice that the parameters here are essentially those that are not associated with your x or your z. Okay, so here we have two parameters. One is going to be your initial distribution, your pi here. Wait, my pen is broken. Okay, one is going to be your pi here, which is your categorical distribution. Then the second one is going to be what is your lambda k here. Okay, so in essence, our parameters now would be, for this set of parameters will depend on one single factor, your pi, for your initial categorical distribution. Then for every single mixture model, we are going to have its own separate lambda k. Okay, because now we notice that we have multiple mixture models, so each of them will have their own set of parameters. That's why we will put, this will be up to a maximum of k different factors for separate lambda k's. Let me put this capital K. Any questions so far? So this is how we will parameterize the problem. At first, I will need to specify the prior. Then afterwards, for every single mixture model, we will have its own lambda k. Any questions? Okay, if no questions, now we'll move on to the second one. We want to determine what is p of xz given theta. Okay, so we want to determine this part is essentially, you can think of it like you will see your this one is similar to your regression model, this kind of your dataset kind of thing. Okay, so second point is we want to determine what is this p of x z given theta. Okay, so for this, we notice that since x and z are basically the entire set of points, right? So we can actually split this down further to saying that this p will eventually depend on, if I multiply the probability of xn and zn for every single n. Okay, so this is telling me that for every single point, I want to find what is the probability of it happening multiply it against every single data points there. Okay, so now this is my product. Once this is done, then I can also split them again by the property of the conditional probabilities. So then I can split this further into saying this will be P of xn given zn and theta multiply with P of zn given theta. Okay, so this part is essentially where I split down this joint distribution down into its own conditional properties, conditional probabilities. Okay, any questions so far? Now do note that this part is essentially what is the prior of your z. Then this part is essentially what is the likelihood. Okay, so once we split them equally, then we can already apply it inside our function itself. First of all, do note that since we have multiple k models, right? Okay, we have multiple k models, so in essence, this will end up being like some kind of a linear combination against all the k models. Okay, so if you look into the lecture definition also, you will be able to notice this pattern. First of all, is for each point, it will either belong to one certain k mixture model or it will not belong to that k mixture model. Okay, so every point n belongs to some k point. Okay, so it will belong to some mixture model. That's why here I can say again, I can put this as another multiplication here. Let me put another color for it to be easier. So I can put another multiplication here, setting it as k. Then inside, I will put down the prior. The prior itself is going to be basically your pi of k. But notice that if I just simply put a multiplication of all the priors, then this will not work. Because the goal here is that I want to determine for this Zn, okay, for this Zn, initially which k is it assigned to, I'm going to get just that prior. Okay, I repeat, for this data point, I will need to see which k is it assigned to at first. Then I'll just get what is the prior for that k. I don't need to handle the other priors of the other case that is not assigned to that certain data point. Else everything will be similar. Okay, that's why here there will be one additional trick that we do. That is for this initial prior, I'm going to raise it by znk. So why do we raise it by znk? This znk will only be, znk will be equal to 1 if zn is equal to k. Okay, if initially your zn is set to be k, then this will be 1, else this will be 0. So the moment that this is 0, everything will be a multiplication by 1. So then it doesn't matter. Okay, so this entire product by k is essentially for me to only obtain the pi k as well as the likelihood for that data point assigned to k, instead of for it to be against everything. Okay, if it helps for it to be easier, you can actually rename the outer k to another variable. That will be easier also. Okay, so in essence, this is basically telling me I'm taking the first prior assigned to just that k. We multiplied with the likelihood just now, which here there will be another multiplication from m equals to 1 up to capital M. This will follow your exponential of xnm given lambda km. Then this whole thing would also be raised to z and k. Because I want it to only work for the label that is assigned to initially. Okay, so this is essentially going to be our p of xz given theta. Any questions so far? Yeah, try to make sense of it that this z and k would be 1 for the assigned label, will be 0 for the one that is not assigned. That's why this product will eventually just be your pi k as well as your product here for that single label. Okay. Okay, then now I can just combine everything into one single how do I say this? I can combine this into one single power. Notice that this part has a z and k, this part also has a z and k. So then I can just combine this to saying that this will be pi k times the product m equals to 1 up to capital M, following this exponential distribution xnm lambda km This will be raised to z and k. Okay, so now this is my p of xz given theta. Any questions? Okay, now third part is where we are going to determine what is the marginal. The third part is where we are going to determine what is this p of z given x theta. Okay, so if you notice, this part is essentially we are trying to apply the base rule already. Kind of like finding your posterior. Initially, we have your likelihood, which is your p of x given z and theta. Then we also have your prior. Then this part is essentially going to be your posterior. So at some point, it should ring a bell that this will be part of your base rule. Then your base rule will actually depend on one part below, which is going to be your marginal. Okay? This is essentially your base rule. So for us to apply directly to our base rule, this part we already have. This part we already have. We just don't have the bottom one, which is your marginal value. So that's what we are going to find now. For us to apply the base rule, we have to find what is the marginal value. Your p of x given theta. Okay? So let's try to find this marginal value together. Notice that x itself, again, this is your entire set of points x. So then I can apply another product here that tells me for every single data point, I find what is the probability of it occurring. Then I just multiply. Okay, so once I have this point, then the next thing to do is where I want to get what is this p of xn given theta. So this is where we are going to do another marginalization here. This p of xn given theta, I can split this further into some probability of xn with some value of z. Okay, I can split this further. From this px, I introduce another variable here, but because I introduce another variable, that is where I will have to do another summation by the total law of probability. Okay, so I notice that I insert another variable here, your z and k. Your z and k would be either 0 or 1, right? Which is for every single possible value of k. So I'm going to put here, for every single possible k here, for every single mixture models k, I'm going to take this probability. So it's either that it will be assigned to mixture number 1, or assigned to mixture number 2, or assigned to mixture number 3, all the way up to mixture number k, as long as in the end there will be one of them that will be 1, right? So that will be your p of xn given theta. I'm going to take the sum against every single probability here. By the total law of probability, this will be equal. Okay, any questions so far? Let me just write here. This is by the total law of probability. Okay, so once this is happening, then we already have what is this distribution. We already have this. So we can just put it inside. And sum from k equals to 1 up to capital K. Now for this one single point, notice that we already have the k assigned to it. So we can just directly put, this is the initial prior, your pi of k. Then we are going to put the likelihood, which is your product from m equals to 1 up to capital M, your dimensions, exponent of x n m given lambda km. Okay, notice here that I don't even have to put the raised to z and k anymore, because now at this point I already assume that I will have a certain k. Whereas for here, initially I didn't have that k value. Here I don't have that k value, so I will have to only point out that indicator value for that certain k. That's why I will put this z and k. So this z and k actually works as an indicator function. That's how you can see this z and k. So this kind of your indicator function. Here, because we already have a given k, then we don't have to use that indicator function anymore. Okay, any questions? Questions? No? Okay, so once we have the marginal value, then we can just plug it in directly, we can just plug into our base rule directly. So our p of z given x theta, by base rule this will be equal to your p xz given theta, sorry, it should be capital Z, over p of x given theta. Okay, notice that this can actually be split further into your p of this can be your p of x given z theta times p of z given theta. Normally we would use this one. For this one, since we already have our p of x comma z, so we don't have to split them again. because we already did in problem 2. So what we are going to do now is to just plug it in from our problem 2. This part is your, from problem 2, this is your product of from n equals to 1 up to capital N, product of k equals to 1 up to capital K, so on and so forth. This is from problem 2. Whereas the bottom one, this is basically the one that we have observed here. So this is from the marginal. Okay. I will not write everything here, so that one I just leave it for you to write up. But this one is from the problem 2, the one that we have observed just now, this part. Then this part is from the marginal that we have computed here. Okay, any questions? Okay, so once this is done, now we are going to find out, this is actually the harder part. We want to find out what is this q of theta with the theta hat. So in essence, we want to determine to which direction should we go after this. Okay, so this is your q function. Your q function is essentially, how do you maximize this? Okay, what do you want to maximize in the first place? That will be your q function. Once you get that, then you get the new parameters that will maximize this q. That is what happens after your m step. Okay, so your e step, your expectation step, is actually to compute this q. Your m step is going to be to maximize this q later on. Okay, so we go on to the e step first. Your e step is to determine what is this q, theta, and theta hat. Okay, so we suppose that theta hat is your set of parameters from the previous iteration. Then we want to determine q of theta with theta hat. So how do we determine this? Problem 4. Q of theta, theta hat. So if you haven't noticed, your q function is essentially similar to your MLE or your MAP. If you haven't noticed that. So your EM is actually very similar to your regression, if you still remember. Okay. So what we are going to do now is your q of theta and theta hat. This part is essentially we are going to apply something similar to your MAP, your maximum a posteriori hypothesis. Okay. Solely because we are going to apply directly to this part, which in the end it doesn't depend on the marginal, so it will only depend on this side. Okay. You can notice this if you see inside your lecture note. Then you will notice that this q of theta and theta hat is going to be, this will be some expectation of, this is your log of p xz given theta. Okay, this part is essentially what is the denominator here. Okay, so what you are trying to do is you want to find out what is the expected value of the log of this p xz. That is what you are going to find. But again, we have to also carefully specify here what expectation do we follow. Okay, here is where it will be a bit trickier. Notice that here, your theta itself now changes its definition into your new parameters, right? Your theta. Whereas your theta hat is basically the current set of parameters. You cannot simply just say, I want to take expectation based on the new set of parameters, because that is where we will actually derive later, right? But for now, your expectation can only be done based on whatever you have in mind, whatever you have observed. That is your z that follows p of z given x and theta hat. That's your current set of parameters. So your expectation can only be done based on your current set of parameters. Okay, that's your keynote here. Any questions so far? Let me just remove this. Capital Z. Okay, so this must be with accordance to your theta hat. For simplicity of this tutorial, I will ignore the writing of this pzx theta hat, but notice that it's always based on the theta hat for this. Okay, so now we just expand this expectation together. So if I write down the p of x z theta, then you will notice that this will be the log of this product from n equals to 1 up to capital N, k equals to 1 up to capital K. Then this will be your pi k, small pi k, then product of all the exponential distributions. Raise it against z of nk. Okay, so we are going to take the expectation of this. But before we take the expectation of this, with respect to z, what we're going to do is we try to see if we can cut this down further to see if there's any variable that will depend on z and any variable that doesn't depend. So if it doesn't depend on z, it's going to be constant, right? Then the expectation doesn't have any effect. We just want to see which part of this whole thing depends on z. Okay, so if I expand this part, then I will notice that log of products, again, you should already be familiar with this. This will be the sum of logs. So now I'll just put this as, this will be sum of n equals to 1 up to capital N, sum of k equals to 1 up to capital K. Now, here, there's a power here, right? So I will put the log of a power, so then the power will be brought down. So now this will be z of nk times the log of whatever's inside here. Your pi k sum from m equals to 1 exponent. Okay, so I'm taking this expectation. Now the moment this happens, then I can just separate by the law of logarithms. Now this will be expectation with, this is your sums. Actually, I'll just skip this part. This will be your log of pi k plus sum of from m equals to 1 up to capital M, log of this exponential distribution. Okay, so now this is basically your expectation value. But we can also split this further to see what is this log of exponential distribution. Here, this is essentially just taking the log of your lambda km e raised to negative lambda km x nm. Okay, so if I take this log now, this will just become log of lambda km plus negative lambda km x nm. Okay, I just apply the log directly here. So products I can separate down to log of lambda plus the log of the exponent thing. Log of exponent is just whatever is on top of the exponent value. Okay, so with this now we already have this whole expectation, which if we write this cleaner one, you can notice here something that this is your pi k. Sorry, let me just write. This is your pi k. This is based on your lambdas, and this is also based on your x. So anything from this log pi k onwards to this point, this actually doesn't depend on your z. I repeat, this log pi k onwards to your xnm doesn't depend on your z. Okay? So the only thing that depends on your z is just this z and k value. Okay? So in that point, I can actually just put this expectation down forward by the linearity of expectation as well as expectation of constants. Then this will just bring down expectation of a sum. Then this will just be the sum of expectations. Okay? Then it will be the expectation of this whole product. But we notice that this log of pi k up to this exponent part actually doesn't depend on your z. So if I take expectation of some constant multiplied by this z, the constant I can bring it forward in front of the expectation. Okay, so I will write the constant first. This whole thing now becomes a constant with respect to z plus sum of from m equals to 1 up to capital M log of lambda km minus lambda km x nm. This will be multiplied by the expectation of z nk with respect to c. Okay, notice that here we brought down this whole big equation, this whole big expectation down into just one small scope. That is, you want to find the expectation of z and k with respect to how z is being distributed, which depends on your current set of parameters theta hat. Okay, so if you remember from the lecture, this is essentially what we call the responsibility constant. Okay, so this kind of your responsibility value. This will end up being what is your delta of z and k. Okay, so let's try to find out what is this delta of z and k. Let's see. This expectation of z and k with respect to z, which is distributed by p of z x following current set theta hat. Okay, this part is essentially similar to just your probability of z and k equals to 1 given x and theta. Why can we model it like this? Because your z and k can only take on values between 0 and 1. Okay, so if I want to find the expectation of this, it will just be the probability that it is 1 times 1 plus the probability that is 0 times 0. Which, this part is essentially just 0, right? Because it's multiplying by z and k equals 0. So I'm just taking out, this is my, it can take values of 1 multiplied by p of z and k equals to 1. So this expectation is just the probability here. which we can expand this further. We can say that this will be based on how the current set is being distributed for your k. So this will be your prior of k. With this is basically your likelihood inside itself. This is your exponent of xnm given lambda km. Okay, this is just for that single k value. This is what is the probability itself. But I'm going to take the kind of like I want to create a new probability here based on this distribution. That's where this will depend on. For every single other mixture, I want to see how is this P of Z and K being created. So now this will be the 5J hat. Then this will be the other sum. Okay. So in essence, what you have seen here is just this part is essentially the part of your PXZ for that one single xnZn. Okay. So this one single part of your PXZ, given that you assume this will be equal to K, then this will be the sum for every single other class. So this is kind of your total sum. This is your current K. Then we just take a probability from there. Okay. So it's your current K. This is your entire sum. Any questions so far? So with this, now this will become our responsibility value. So anytime you see this delta of Z and K, you can assume that it will be this fraction. Okay. So we can rewrite our Q function now. We can rewrite this Q using our delta. Now this will just be the sum of n equals to 1, sum of k equals to 1 of this delta Z and K with the log pi k plus sum of from m equals to 1 log lambda km minus km log minus lambda km xnm. Okay, remember that here whether it's a hat or not is important, because the reason why this is a hat because it depends on the current set of parameters, whereas this one depends on your theta, your new set of parameters. Okay, so notice the hat and the no hat. Any questions so far? Now once we have the Q value, the last part is where we can just find out how do we maximize this. To maximize this, that's where we will utilize your derivatives. So we just need to set the derivative of this Q with respect to a certain parameter. This should be set to 0. Okay, but notice that the parameter here will just depend on how you iterate forward, which will depend now on how your mixture models is being updated. Okay, so this will depend on how you iterate forward. Then it will depend on how your mixture models is being updated plus how your priors are being updated. Because later on again, this categorical value, the way that you are assigning your case, the way that you are assigning your n data points to different models, this will change the moment you change the mixture model. So the moment I shift the mixture model around, some points might actually be reassigned. That's why the prior will also change for that. Okay, so it will depend on two things. One is how the mixture model will change. The second one is how the prior itself will change, which is your pi of k. Q would be 0. Okay, depends on these two things. So let's find out the first one. First one is we will actually differentiate it with respect to your lambda km. Let's set this to be equal to 0. Put this as Q. Okay, if I set this equal to 0, then I will notice here that the one that depends on this lambda km is just going to be this part. Okay, because your delta of Z and K depends on your lambda hat, not your lambda km. Okay, it depends on your lambda hat. Depends on what you already set. What we want now is to set a new one. Okay, so it doesn't depend on your delta Z and K. So this will be a constant, treated as a constant. Then we just take the partial derivative with respect to this. So now this will be just your n equals to 1 up to capital N, k equals to 1 up to capital K. Your delta is now a constant. Then now this will be your, we differentiate this part. So now this would be here. Before this, I also need to emphasize here that if we are going to differentiate it with some delta, with some lambda km, right? That means it will only work for one single k value. So here we notice that this will be sum up against from k equals to 1 up to capital K. Or easier to see, if you change this to some certain variable p equals to 1, now this will be your Z and P, this will be all p's, right? notice that the moment you differentiate with respect to lambda km, it will only work when p is equal to k. Okay? Because the moment that p is not equal to k, then this zn will already be 0. Okay? So it will only work when p is equal to k. That's why this summation here, this summation will actually no longer work. Because if you assume that this will be like some p, there will just be when p is equal to k, then this will have the certain value. So now this will be your delta of znk. Differentiate this part. So now this will just be, if you differentiate this part with respect to lambda km, notice that since we set an m also, then this summation will only depend on one certain m value. It will not be a sum of every single m's here. Okay? So if I change this to some other variables, let's say if this will be like some j, then it will only be when j is equal to m that it has a certain value. So this summation will also be out. Okay? So with that, then I'll just differentiate this log of lambda nm and this part already. So this will just be lambda nm minus this will be just your xnm equals to 0. Okay? So the summations are out because we set for certain k and m. Okay? Now once this happens, then I'll just split out the sums together. So now this will be the sum of n equals to 1 delta z and k times 1 over lambda nm minus sum of n equals to 1 delta z and k xnm is equal to 0. Which here I can just move the xnm side to the right side. So now this will be equals. Hence I can just plug this 1 over lambda n outside. N equals to 1 up to capital N delta z and k is equal to this whole summation. Okay, so this part, since your delta itself is an expectation of this z and k, so this will tell you that assuming your current n, this will tell you whether this one certain data point is expected to be z and k equals to 1 or not. Okay, so if I take it against every single data point, then in essence this is just simply adding the probability of each data point being z and k equals to 1 for every single data point. Or rather, this will actually show you out of every single data point, how many data points are actually k set to z and k equals to 1. Okay, so this is basically your nk. Thus, I can actually have this lambda km already. So this lambda, so this should be lambda km. Yeah, so my lambda km now is essentially just transposed away. This will just be nk over this whole summation. Okay, so now this is my lambda km. Once I found out the lambda km, the last part is to actually determine how to get this pi of k. Okay, so now we want to determine how to get the pi of k. Set this pi of k to be equal to 0. However, the pi of k is a bit difficult because there's a certain constraint. The constraint is such that I want to ensure the sum of this pi k must be equal to 1 for it to be a categorical distribution. Okay, so there's this constraint that I have to set. Because of this constraint, then the logical thing that comes to mind is to set this as a Lagrangian. This will be my Lagrangian multiplier. So set this constraint as minus 1 equals to 0. Then I'll have this will be my Lagrangian. My q plus, set this to be nu sum of pi k equals minus 1. I want to differentiate this. Okay, so now this will form a Lagrangian because I have a constraint that my pi k sum it up must be equal to 1. So when I do this, then I can just get the derivatives directly. Notice that here, I want to depend on my pi k. So if I depend on my pi k, then it will only depend on this log of pi k, which is multiplied by this z and k. Okay, so if I differentiate that, then we'll notice that this part is just simply, you can check this further. This will be 1 over pi k times the n equals to 1 up to capital N, your delta z and k. Plus, if you differentiate with this with respect to your pi k, then this will just give you your Lagrangian multiplier. This will be equal to 0. Okay, you can check this differentiation later. So this part, as we have seen just now, this is just how many data points are assigned k. So you can set this as 1 over pi k times nk plus your nu, your Lagrangian multiplier is equal to 0. That's why you will get your pi k itself is just negative of how many data points are assigned k over the Lagrangian multiplier. Okay, so this is your pi k. Once I get this pi k, I can eliminate the Lagrangian multiplier by inserting it to the constraint. I notice that the sum of all pi k's must be equal to 1. So I'll plug this in inside. Then I will get this will be, this part is just I want to sum this up. Negative nk over nu must be equal to 1. This nu doesn't depend on the k, so I can just plug this outside. So notice here that nk is how many data points are assigned k. If I sum this up against every single possible mixture, then this will already give me how many data points are in total. So now this will just be your negative n over nu. In other terms, you can set that your Lagrange multiplier nu is going to be negative n the moment this reaches your maximum point. Okay, so once you get that Lagrange multiplier done, then now I can just update my pi of k. Pi of k is equal to negative nk over this nu, which is negative n. So this is essentially just telling me nk over n. Your proportion of data points assigned to be k over your n. So that's your pi k. Okay, if you want to be exact also, you can actually just split your nk further into saying this is your 1 over n. This is your, back again to your delta, your responsibility value. Okay, so in essence, what it shows now is once you already apply your maximum step to get what is your next lambda and pi values, that is where you get your, this is your pi k value to be applied next, this is your lambda k value to be applied next. That is essentially the purpose of this step. Okay, so just repeat this until it reaches a convergence, then you are done. Okay, then you have your model ready. Okay, any questions? No questions, then that's it for